of air, heat, and so on, humidity, for example. These are arrays of sensors which are battery-powered, limited computational and communication capabilities, and of course intermittent communication. Since they are battery-operated, the sensors are not active all the time. There are base stations that collect data and control the operation of the sensor. So we have two kinds of base stations, or a base station that has two types of functionality. And in fact, some of the base stations that we have are likely to be mobile. So sometimes we do have users doing readings of these sensors and controlling their operation. Now, in terms of the sensor networks that I'm talking about here, there are some differences of the new sensor networks that I'm talking about and the old ones. What are the differences? One is scale. Imagine an array of sensors that has 10,000 nodes as opposed to 100. Also imagine that the sensors that I'm talking about, these nodes, the 10,000 nodes, are deployed in an ad hoc manner as opposed to a pre-planned location type, location by location deployment. So for example, these sensors could be scattered on a field completely randomly. The extension of the network that I'm talking about could take place without involving any administrative intervention and without having any trusted third party. The environment in which this network is going to be used, it's also different from the environments that we've seen before. These environments could be hostile. Namely, the sensor activity can be monitored, the sensor can be captured, they could be replicated, they could be inserted in the network, and then input could be manipulated. So this is sort of the kind of new technology that I'm postulating. Now, I've seen a couple of networks like this. They are used in defense, but you could have something similar to this. So the claim is that this kind of new technology introduces new and unique vulnerabilities, and the adversary that we have is different, and consequently we require new methods and tools to cope with this adversary. In particular, we have what's called emergent algorithm and emergent properties to deal with this adversary, which are basically probabilistic properties of the system that we try to make happen. Now, there are other examples that do have the same characteristics other than sensor networks, like mesh networks. People are postulating vehicular networks, which are probably the most realistic example of ad hoc networks. And those networks might have similar, in fact, do have similar characteristics. Okay, so let's see why these sensor networks that I postulate have this problem. In other words, what causes these networks to be vulnerable to this new kind of adversary? And in fact, what causes these networks to be vulnerable is their very success. Just like with the internet, the very success of the internet enabled new adversaries. So what do I mean by success here? Well, one is that these networks are very easily deployed and extended. In fact, they are very scalable. You simply drop sensors at desired locations or desired areas, and these nodes would establish connectivity and key connectivity, because obviously you have to use crypto to encrypt the data and protect the integrity of the data between nodes. They establish this key and network connectivity on their own. No third party, no trusted third party, no administrative intervention, no base station intervention. They are low cost. Basically, these nodes could be built with technology that you can buy at Radio Shack, and they are very low cost. In fact, a node could cost roughly under $10. The processor might cost $1. Then the sensing type of equipment would cost maybe a little more, but overall, each one of them would cost under $10. So you could easily have $10,000 nodes being deployed. The problem is that this low cost causes the vulnerability of not being able to shield these nodes. Why? Because node shielding, the technology to shield these nodes, both the sensing part and the processor part, is maybe about 3 to 4 orders of magnitude more expensive than the node itself. So for example, if you look at the top of the scale of shielding technology, you might find something like the IBM 4758, which is this very highly protected card, which is shielded through various layers of metallic shielding and resin shielding, that has inside the box, inside this card, you have temperature sensors, ionizing radiation sensors, voltage sensors, pressure sensors that have their own battery and has an erasable memory, battery-backed erasable memory, such that if somebody tampers with the box, the memory disappears. This costs about $4,000, right? It's very sophisticated, very nice protection. It's level 4 physical protection on the NIST FIPS 140 scale, but it's very expensive. You cannot really afford this for each one of the sensors that you deploy. Okay, so what can happen? Well, first of all, before I tell you what can happen, let me show you just one example why keying is so trivial in key connectivity is trivial in the sensor network. So imagine that you have a neighborhood of sensors like the ones seen here. So you have 6 sensors in a neighborhood, and these sensors are keyed in the following way. So we are going to use a probabilistic key redistribution scheme. This is one of the many that have been proposed. In fact, happens to be the first one. Not necessarily the best one, but it's certainly the first one. So imagine that we have a pool of random keys. This pool could have roughly about, say, 1 million keys. That's about 2 to the 20 keys, right? Out of a space of 2 to the 128, the 2 to the 20 keys is a very small pool, of course. So you have a small pool of random keys. And out of this pool, you draw k keys, where k is a very small number, say 75 to 200. So you randomly draw, say, up to 200 keys, fixed number, and you insert those keys, you store them into the memory of the first sensor out of the 10,000. Put the keys back into the pool, draw randomly another k keys, say 200 keys, install them in the second sensor, put them back, and repeat the process 10,000 times. This is offline, right? After you've done this, throw the sensors randomly on a field. Well, obviously, you are going to get in the random drawing of these keys from a fairly small pool of random secret keys. Obviously, you are going to get some collisions. So obviously, you are going to get some shared keys between nodes in the same neighborhood. Not between all nodes in the same neighborhood, but between some. And then you can play with your parameters, with k and with p, to increase the sharing or decrease the sharing. Okay? So these lines that you see between the sensors, between the yellow sensors, represent the keys that happen to be shared between nodes. And what you notice is that some lines have the same color. And that's a very unfortunate effect because, for example, if node B receives via the blue keyed connection a message which is MAC'd, namely has a message authentication code with it, the B node will not know whether that MAC'd message comes from the southernmost node or comes from one of the 2 northern nodes, which also share a blue key. So this essentially says that node-to-node authentication is no longer guaranteed. This clever scheme that I described has this drawback among others. However, we can mitigate this, and the mitigation is a subject of a different talk, but we can mitigate this drawback. The point of this example is that we pre-keyed these nodes, we randomly scattered them, and the nodes themselves broadcast